Hi kids, Miss Block here, and thanks for joining me today as we discuss density. Ready? Let's get started. So what exactly is density? Density is the amount of matter in a given space. So if we were to look at this diagram right here, all the way on the left, you can see that we have a few atoms in this box, and they're fairly spread out. They're not crowded. It doesn't have a very high density. Instead, it has a very low density. As we move to the right, you can see that there's more and more atoms, and it's getting more and more crowded. Right here, we have a lot of atoms in this space. It has a very high density. We have more matter in that given space as compared to this on the left. We can see this often when we look at a density column. So in this picture right here, I know, pretty colors, right? We have this red liquid floating on top of all the other colors. The reason it's floating on top is because it has the least amount of matter in a given space. It has the lowest density. Likewise, that purple liquid on the bottom has the most amount of matter in a given space. It is the most dense. So if we recall our picture from before, the atoms are spread out in this red liquid compared to the atoms in this purple liquid. They're going to be more compact. This kind of applies to this problem we're going to look at next. This might look a little familiar, so try to answer it now. Pause the video. I'm going to keep going. So in this example right here, we're asking what would happen to a piece of quartz as we drop it through a density column. And we're going to ask where this quartz that has a density of 2.7 grams per cubic centimeter is going to do. What's going to end up with it? The answer to this problem is actually going to be D. It's going to pass through W, X, and Y, but not Z. The reason is because the density of the quartz is 2.7 grams per cubic centimeter. While W has a density of 1 gram per cubic centimeter, X has a density of 1.8 grams per cubic centimeter, and Y has a density of 2.3 grams per cubic centimeter. So the atoms in W, X, and Y, they're spread out more. They're much less dense. They're going to float or allow the quartz to pass through. However, Z has a much greater density. Those atoms are much more crowded together. Okay, there's much more matter in a given space for Z. So the quartz will actually end up floating on layer Z. It will not pass through. Density has many applications in earth science, or we look at it, and it influences a lot of different earth processes. For example, if we were to look at the layers of the earth, and you think back to that density column we looked at, the earth itself is like a giant density column. The denser materials are towards the center of the earth, and the less dense and least dense materials are closer to the surface. If we were to add the water and the atmosphere on top of that too, you would even have a greater density column. All right, because the atmosphere is resting on top of the hydrosphere. Now, density can be expressed mathematically through the following formula. Density equals mass over volume. And that's why before that definition might have sounded familiar, because we kind of combine these two factors together. Mass, remember, is the amount of matter in a given space, and we express mass in grams, and volume is the amount of space an object takes up. And we can express that either using cubic centimeters or milliliters. Let's look at another sample problem. Oh, before the sample problem, remember you could find density on the front page of your reference tables, that equation. So what you need to know is right there. You do not need to memorize this formula. Now let's try a sample problem. So shown to the right, we have an empty 1,000 milliliter container has a mass of 250 grams. When filled with a liquid, the container and the liquid have a combined mass of 1,300 grams. What's the density of this liquid? Take a moment to solve it out. Pause it. I'm going to keep going. This is the solution to it. So the answer is actually going to be B. Taking my equation for density, so it's going to be density equals mass over volume. Now I have to find the mass of the liquid. I know that the graduated cylinder has a mass of 250, and then the graduated cylinder and liquid have a mass of 1,300. So if I take 1,300 and subtract the mass of the graduated cylinder, I'll get the mass of just the liquid. And that works out to being 1,050 grams. I also know since I filled the graduated cylinder, I'm going to have a volume of 1,000 milliliters. So I take 1,050 grams divided by 1,000 milliliters, and I end up getting an answer of 1.05 grams per milliliter. And my answer ends up being B. Sometimes you're asked to manipulate a density formula. So they'll give you density and you need to find mass, or maybe you need to find volume. They'll give you two of those variables. So you can use something called a density triangle if you have trouble manipulating equations. Now, the key is that you have to memorize where all the variables go in the triangle, because if you don't, you're going to mess up. As always, I do recommend doing the math out, but I know some of you do struggle with math. So for example, if I was looking for the mass, I would cover up that mass, and now I'm left with density and volume. Since in the triangle they're next to each other, we're going to multiply them. So we end up getting mass equals density times volume. Likewise, if I was looking for volume, I cover up the V, and I see that mass is over density. So as a result, volume equals mass divided by density. Now, if I change the shape or size of an object, does its density change? Let's take a look at these two items right here. Aluminum foil. We should all be very familiar with that, right? So, on the left I have a roll of aluminum foil, and on the right I have bars of aluminum. Now, which one's more dense? You might be inclined to say the bars of aluminum, but since they're made of the same substance, there's no change in density. They will have the same ratio of mass to volume, so they have the same amount of matter in a given space. Let's take a look at this graph. This is not aluminum, but instead this is pyrite. All right? And I've taken 5 samples of different sizes of pyrite, and they've been plotted on this graph. So let's say we looked at a smaller sample of pyrite. Right? It had a mass of 50 grams and a volume of 10 cubic centimeters. I solve out its density, and I find that it's 5 grams per cubic centimeter. Now I'll take a bigger piece of pyrite, one that has a mass of 150 grams and a volume of 30 cubic centimeters. I solve that one out, and I find that its density is 5 grams per cubic centimeter. So while the size might have changed, and while one might have felt lighter because it was just smaller, the ratio of mass to volume has stayed the same. I will still find the same amount of matter in a given space in each sample. Their density is the same. There is no change in density. Let's take a look at this sample problem. Pause it, solve it out, but I'm going to keep going. So we're looking back at our old friend aluminum here, and a student calculated the density of 5 different pieces of aluminum base, each having a different volume. Which graph best represents the relationship? So they had a different volume, they were each a different size. However, they're all still aluminum. They haven't had any changes to them. So as a result, the density should not change. So we want to find a constant relationship, and that would be A. As the volume increased, the density stayed the same. Now, there is a way to change the density. And to change the density of an object, we need to find a way where we can change the volume without changing the mass. Because if we can change the volume, we can cause the matter to become more compact, squish those atoms together more, or we can go and we can make those atoms spread out, increase that volume. And this can either be done by a change in pressure or a change in temperature. Pressure, all right, as I increase the pressure on an object, the volume will decrease. An inverse relationship. Since the volume is decreasing without a change in mass, the density will increase, thereby causing a direct relationship. You can see that right there. This happens with metamorphic rocks. They increase pressure on them, and the atoms get more and more compact. As a result, they will be much more dense. Temperature works in the opposite way. As temperature increases, the volume will increase. Since the volume is increasing, those atoms can really spread out. And as a result, the volume is increasing without a change in mass, the density will decrease, giving us an inverse relationship. That's why if you think about it, when you have like a hot air balloon, you're heating up that air and the molecules are spreading out and they're getting warmer and warmer, and the hot air can rise up. However, water is kind of a unique substance, because if you think about what we just said, Substances should be most dense in the solid phase, but that's not the case as illustrated by our picture here because the ice is floating. All right? So if most things should be most dense in the solid phase, ice is floating in water, thereby signaling that it must be less dense. Well, think about this with water when it freezes. When water drops below 4 degrees Celsius, that's when water's most dense, 4 degrees Celsius, okay, or 3.98 according to the reference tables, it will start to freeze. And if anybody's put a can of soda in the freezer, what happens to that can? It explodes. Why does it explode? Because the water in the soda starts to expand, all right, increasing the volume instead of having the volume contract or shrink. All right, so as water freezes, it expands, the volume is increasing, thereby making it less dense than liquid water. Hopefully, this video is able to help you out and you got a lot from it in understanding density. Feel free to watch it again or come to extra help. I'll see you again soon. Take care. Bye-bye. I have a special guest who made it all possible because they took a little nap. Say hi.
Nope.
Nope. Okay. This is what happens when they just wake up. I love you, boy.
Are you boy?
Oh.